Hi there, and welcome to a Calc 2 video where we are reviewing the inverse trig integration formulas from Calc 1. Possibly some of these weren't really mastered in Calc 1, so let's go ahead and start from scratch before we look at those U-sub versions. So let's just say I was asked to find the antiderivative of 1 over the quantity x squared plus 1. So that sum of squares there in the denominator. And certainly that dx could be written in the numerator as well. We should recognize this as being the inverse tangent of x plus c, or we could write that as arctangent of x plus c. Okay, well, let's just do one at a time. Let's just add one thing in so we can see how the pieces of this are all going to fit together. Let's just say instead of the quantity x squared plus 1, let's say I have the quantity x squared plus 4. Well, in order to make this inverse tangent of x, I need to have that constant be a 1. So let's go ahead and factor a 4 out of my denominator. So it looks something like this. Then it would be x squared over 4 plus 1 as my quantity in those parentheses instead. And we certainly know that the other way that we could write that was by putting that 1/4 constant coefficient out front. So I have something that looks like so. Okay, now what? Well, now I can use my U substitution to make it look like the general antiderivative that we knew was inverse tangent of x. So I'm going to figure out here, what am I squaring to get this x squared over 4 quantity? And I should be able to see that I am squaring x over 2. Okay, so that's just a rewrite that maybe will help us see our next step. So I'm going to let u be this x over 2. So then my du is just 1/2 dx. So I will multiply in a 1/2 and out a 2, because again, we can't change the value of our antiderivative, but we can certainly change the way that it appears. So then I see I have a 1/2 out front, 2 times a 4th, and now I really have 1 over the quantity u squared plus 1 du. Well, that is my inverse tangent of u, but of course I have that coefficient of 1/2 out front, and u was the x over 2. So let's see if I can maybe make some generalizations. If I look back at the original here, I had the antiderivative of 1 over the quantity x squared plus 4. And if I think of it in terms of, 1 over, let's write it in the same order here. So if I have 1 over u squared plus a squared, and I'm integrating with respect to u, I can see the a, or the constant value, is what I'm squaring as a constant. The u would be what I'm squaring as a function. So if the only difference is that I have a 4 or a 9 or even a 5 instead of that 1, I can see that it's what you're squaring variable-wise, so that u over what you are squaring constant-wise in that denominator. So if you look at those two terms, it would have been 1 over this x squared and a 2 squared. Right, so looking at where did that x go, well, that's the variable that I'm squaring, so there's the inverse tangent of that, and then over the constant that I was squaring here. And again, this 1/2 comes into play because I have that 1 over a, or what I was squaring as a constant, as a coefficient. Again, your u substitution gets you to the same place. So let's look at a different one where now I have antiderivative of 1 over 9x squared plus 1. So now I still have that plus 1, which is great. But now what I'm going to say is I'm going to look at this as a quantity 3x squared. because then I can see my u substitution pretty quickly. U would be 3x, the inside of that function squared. So du is 3dx. I can multiply in a 3 and out a 1/3. And if I do my rewrite, I have 1/3 antiderivative 1 over that quantity 3x squared would be my u squared. I still had the plus 1, and it's du. So this turns into just 1/3 inverse tangent of u, which is 3x plus c. So again, I can see now the difference is my 3x, well, that's because I was squaring a 3x, right? So that's that numerator, that's that u value of what you were squaring. I'm going to write over 1 just for a second here, and see that's what you were squaring as a constant. But I always do have to be evaluating this leading coefficient because that will come from my u substitution as well. So I'll do one more, but we'll piece them all together, and that one is actually on our notes. So maybe that helps you with that formula, maybe not. Again, the one thing I want to make sure that you recognize is, do you see there's no u prime here in what this antiderivative equals? So it may not be complete just leaving it on its own. So let's make sure we always identify what our u is and then find our du. Okay, so in looking at number 1 here, or this first example, I am going to move this constant coefficient of a 6 out front. So this is just a quick rewrite of this antiderivative. And then I'm also going to see it as 49 plus 4x squared. Well, I can recognize, right, that this is a 7 squared and this is a quantity 2x squared, and that might help me in the future. I do need this to say 1 plus or plus 1 as a constant. So I need this 49 to be factored out. So I'm going to rewrite it as 6 over 49, because the over 49 can be factored out to the front. So then this is a 1 plus, and I'll just write it right now, 4x squared over 49. So now when I look at that, this is really the quantity 2x over 7 squared, and that's what I'm going to let be my u. So u is 2x over 7, so du is 2/7 dx. And again, I hope this is somewhat of a review for you. You just might not have seen it in this form. So I will multiply in a 2/7 so that I have my du up here, and I will multiply out a 7/2. And yes, it will be very obvious to you that you're doing it right, because you will see that those should divide or simplify pretty nicely as you go through. So that'll leave a 7 and a 3. So I will have a 3/7 on the outside, and on the inside, or in my integrand, I have du, right, because that's that 2/7 dx, over 1 plus u squared. So that would be 3/7 inverse tangent of u, and my u is 2x over 7 plus c, and you are done. Okay, and the 6 maybe makes it so you're not seeing that u substitution in there, or what was left over. So if I didn't have the 6, that 2 would have still been there, and I would have had, 1/14. So I'm going to do the next one using u substitution, just so you can see how it looks all the way, kind of start to finish here. So this one is going to be derived from our inverse secant, or arcsecant. Some people prefer to write arcsecant instead of whatever argument, instead of inverse secant. Again, if we ever mean to reciprocate a trig function, we would write it as its reciprocal name. So for example, I will never write cosine of x to the -1 as an exponent, meaning to reciprocate, because that is secant of x. If I reciprocate cosine, I get secant of x. So some people just prefer to write arc secant, arc cosine, etc. to again lessen that confusion of what's an inverse trig function and what is an exponent. But we really don't write trig to a negative exponent because they have names. We can reciprocate. So if I'm looking at this integrand for the formula, I can see that I have a difference of squares where u is some function squared, a is a constant squared. So I can see here that my u will be 3x, hopefully you can see that. And then my a, yes, will be 11 because that's what I'm squaring. But let's make sure we have our a, and that's fine, that's a constant, but I want to make sure that I account for my du as well. So du would be 3dx. So again, I'm going to multiply by 3 on the inside, so I will multiply by 1/3 on the outside. And that way now I have 3dx in, which will become du. I'll talk about the x here in a second, but I would have square root of that 9x squared is going to become that quantity u squared minus my a squared. So it is looking like that arcsecant formula, although what goes right here? Well, that's x. X is, solve your equation that you wrote. You can use this at any time, as many times as needed, especially if we're changing bounds or things like that. We might need it more than one time. So if u is 3x, then x equals u over 3. So that's what this will be, u over 3. And then I'm going to get lucky because dividing by 3 here in the denominator, I can bring that out as multiplying in the numerator. Again, multiply by the reciprocal if you want to think of it that way. So I may not have actually noticed, but I did deal with the u substitution. This is what I have now, and that is exactly my inverse secant formula. So I have 1 over the a, which was 11, arcsecant of absolute value of your u, which was 3x, over 11 plus c. Okay, so if you just do your standard u substitution, all will fall into place. We just have to make it sort of match some of these integration formulas that we should know from Calc 1. Hopefully you found that video helpful, and thanks for watching.